Hello everyone, welcome to the second lecture on operational amplifiers. In this lecture, we are going to do first a quick review and then we will move on to different types of operational amplifiers. So let's first see what we discussed in the last lecture. We talked about the basics of op-amp, and then we saw different use of op-amps, its applications, and then we saw this symbol. This is your operational amplifiers. We talked about different pins of the op-amp, and then we saw the internal circuit of the op-amp. That's what is there inside this op-amp. And then we discussed the simple model of the op-amp. And here, this is a very important slide. It says the open loop gain in case of an ideal op-amp is infinite, and input resistance is also infinite, and output resistance of an ideal op-amp is 0 ohm. And these are the values of a typical range when you consider a practical operational amplifier. And then we discussed this problem considering uh, considering a case where we did not include the properties of an op-amp, and we solved this circuit for V0 and I0. And this is the same thing, ideal op-amp properties, very important slide. And then so this is your virtual ground concept. I did not use the term virtual ground last time, but what you see here is basically this concept which we discussed is called your virtual ground, which means when your gain is infinite, then V plus is equals to V negative. So this is your virtual ground. And then using the ideal op-amp properties, we discussed this example, and then we found the value of I0 and V0, which was the same, similar to what we found in the last example. But the only differences here, we considered the properties of the operational amplifier. And then we discussed the inverting op-amp, where in the inverting op-amp, you provide the supply to the inverting side, and at the output side you get the inverted signal when compared to the input. So whatever the signal you give here, you get the inverted signal at the output. And this was the very important equation to find the output voltage in case of an inverting op-amp. So where is the feedback? We discussed this. This is your feedback, and it's a negative feedback. So some portion of the output voltage is going into the input of an op-amp. And then we did a quick review. It's the same thing. Now we are going to see the non-inverting operational amplifier. So an op-amp can be used as a non-inverting op-amp when the supply is given to the positive side of the op-amp. So you see here the supply is given to the positive side of an op-amp, and the feedback is provided through this to the negative side. Okay, so in this case, your output is not inverted, and that's why it says non-inverting. So whatever the direction of the input is, the same direction you'll get the output signal, and the signal will not be inverted, but the signal will be amplified. Value you will get at the output. So this is the non-inverting op-amp, and now we are going to see how to find the equation for output voltage for this particular circuit. So the first thing we'll do to find out the output voltage for an non-inverting op-amp is that you apply the KCL, Kirchhoff current law, at the inverting input. So this is your inverting input, because this is negative. So this is your inverting side, and at this particular point we are going to apply the Kirchhoff current law, which says the algebraic sum of all the currents at a particular node is equals to 0. That means so I1 plus I2 minus I negative is equals to 0. So we will use this KCL equation next. So I dash or I negative is equals to 0. Why? Because we are considering the ideal op-amp properties, which means the input impedance is infinite. So that's why your I negative is going to be equal to 0. So this is 0, and then these have some values. So let's see. I1 is minus V dash upon R1, where what is this? Okay, so I1, so this I1, this is your I1 is equals to minus V, this dash upon R1. Oops. So the voltage here, so voltage at this particular point, just one second. Okay, so this is your V negative, you can say. That's your node. This particular node is your V negative, and we are trying to find the I1. So I1 is so this minus this, but you see that this current is going inside, so this is going to be negative V dash upon R1, and that's what you see here, negative V dash upon R1, which is equals to negative V in. So V dash, this is equals to V in. Why? Because we are considering the ideal op-amp property, where so let's write it here. So where this V dash is equals to V in, this is the property of a virtual ground. Okay, so by this property, the voltage which is here is your V negative, and that's the same voltage is coming here, it's the same node, and then V in is this voltage which is going in here. So by the virtual ground property, these two are going to be equal, and that's the reason we have written here V in. Okay, now okay, so now we have I2 we have to calculate, and so this is your I2, and I2 is going here inside this node. Okay, this is also going inside, so this is going to be negative V dash minus V naught upon R2. So that's what you see here. So this negative, so negative like whole negative. So let's maybe quickly use this. So here for this particular, you will get this equation, negative V dash, and then this is a negative sign, this is a big negative sign, and this is V naught up, and this whole divided by R2. So what you are going to get here, you will get V naught minus V dash, and this is whole bracket divided by R2. Okay, so this is what you are going to get, and that's the same thing. If you notice, this thing is same like here, V out minus V dash, where V out minus V dash, where this V dash is your V in, because we learned here by virtual ground these two voltages are going to be equal, right? So now we know the current in flowing in this branch and current flowing in this branch, and we know this current is 0. So now we know all these three currents. So this is 0, this is I1 is minus V in upon R1, I2 is V out minus V in upon R2. Now what next we are going to do? We are going to add these three. So adding these three, we will get this value, which is equals to 0, and since the algebraic sum of all the currents is equals to 0, that's why we have this equated equal to 0. Now simplifying this equation and finding in terms of V out and V in, you will get this equation. So this is the equation for a non-inverting operational amplifier, and this equation is very important. So this equation and the equation which we saw for inverting op amp, they are extremely important. Because if you remember these two equations, then and you are given the circuit with R2 and R1 resistance, then you can just plug in, and you know the input voltage, then you can just plug in the values and you can easily calculate the V out, where this R2 is basically your feedback resistance. So this R2 is the feedback resistance, right? So yeah, this is your non-inverting op amp, and this is the equation which has been derived from the circuit by applying the KCL. So always remember that in most of the operational amplifier circuit, you will be using this KCL. You will be applying this to find out the output voltage. Okay, now next is our voltage follower. So as I said in the first lecture that op amp can be used as a voltage follower, and this is an example here where you see that input voltage is given to the non-inverting terminal, and if your negative feedback, if you don't use any resistor, you just wire up like this, then what it's going to become, it's your voltage follower, which means your output will basically get whatever is there at the input of an op amp. So this is behaving like a buffer, right? Because whatever you are giving in, you are getting the same output, the same at the output, and with the help of op amp, you are getting the constant output voltage. Okay, so so that's your voltage follower. And now let's see next. So here, this is another type of operational amplifier, and this is called inverting summer op amp. We say it inverting summer because the input voltage is supplied to the inverting side, and the output voltage which you get is basically inverted output voltage you get in this particular case. So inverting summer, so which means there will be a number of inputs which will be summed and goes into the op amp. And that's what is happening here. So V1 represents your input voltage, V2 is also input voltage, and then you have V3. So these are the three input voltages which are connected to the input resistance. So R1, R2, R3 are the three different resistance connected to these three input voltages, and they produce a current I1, I2, I3 which goes into this feedback circuit where RF is the feedback resistance, and then when the current goes in here, then you have some output voltage over here. Okay, so now since we know how to solve, how to simplify the equation for output voltage in inverting and non-inverting op amp, so you can just use the same method and apply into this particular circuit and find out the equation of the output voltage. So since we already derived the equation for inverting op amp, so this is going to be very similar to that. So KCL at the inverting input. So these are your three inputs, and these are the three input resistances, three currents, and then feedback circuit. Okay, so we can apply a KCL at this particular node. So at this node, you know that what is the value of this node? This is going to be 0, because if you see, the non-inverting side of an op amp is grounded. So by the ideal op amp property, we will have the V negative voltage will also be equals to 0. So these two are going to be 0. And then at here, we are going to apply the Kirchhoff current law, which means algebraic sum of all the currents at this particular node is going to be 0. So I1, I2, I3 are going into the node, and then IF is going out of the node. So let's see next. So in this slide, we have calculated all the input currents. So if you notice this, the input current I1, I2, I3, they are going to be same, only the difference is you put the different voltages and different value of resistance into the equation. So I1 is what? I1 is equals to your V1 minus V dash upon R1. So where V1 is what? V1 is this at this particular node. So sorry, this is your V1 and this is your V dash. So V1 minus V dash upon R1. The reason why we are taking in this way, because our current is flowing in this direction, so that's why V1 minus V dash. You can take it the other way also, but you have to put a negative sign outside, and then you can say V negative minus V1. Okay, so V1 upon R1. So V1 minus V dash or V negative upon R1, and then same V2 minus V dash or V negative upon R2, and here same V3 minus V negative upon R3. So you see, or V dash you can use. This notation doesn't matter. You can use any notation. You can either use it as V4 or V negative uh, or VA, or and this as VB. It does not matter. The most important thing is which is matter is that you understand the properties that these two nodes, these two voltages are equal, considering this as an ideal op amp. So we have three equations of currents, and then we are going to put it into the KCL equation for this particular node. Okay, and I dash is equals to 0. We already know this. Why? Because this is the current going into the op amp, and since op amp has a high infinite input resistance, so this current is going to be 0. So what we will get, you will put all these equation equals to IF. So let's see here, I1 plus I2. So it's going to be like this. So by KCL, you will get this particular equation, I1 plus I2 plus I3 at this node will be equal to IF plus I dash. So I dash is your 0, and IF we will see is basically the difference in the voltage from this to this upon RF. Okay, so which means you can say V negative minus V naught upon RF, right? So that's what we are going to see here is your, okay, so they have taken the opposite way. They have taken in this way V naught minus V negative upon RF. The reason why they have taken, because here they have taken opposite way. What I mean is they have taken the current in this way, V1 minus V dash upon R1, and V2 minus V dash upon R2, and V3 minus V dash upon R3. And for here they are taking V out minus V dash upon RF. So that's also correct. You can take this way. Otherwise, you can also the take other way, where this will be negative and this will be negative and this will be positive. But then you have to make sure that you are taking the convention from here to here. Okay. So all in all, you will get the same result, and the result is this: V1 by R1 plus V2 by R2. So all the currents are added, plus this IF current is added, is equals to 0. So ultimately you will get output voltage is equals to minus RF by R1, V1 minus RF by R2, V2 minus RF by R3, V3. Okay, so right now, like, we have drive this circuit and found out this equation. You can directly put the value of all these different resistances and feedback resistances into the equation of a simple inverting op amp. So simple inverting op amp, what does it says? So it says your let's see, let's write down that equation here. So simple inverting by inverting op amp, we can say that V out is equals to negative of RF divided by input, right? So in this particular case, what we did, your feedback resistance is common. If you go back and see, look here, RF is common. What is changed is the R1, R2, R3, and all these three input resistances. Okay, so I missed the V in here, so I should put V in here. So that's what we did. So if you apply all based on our circuit, the same thing you will get. So you will get RF is equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and whole multiplied by so each voltage is also different, so you will have to multiply by, this will be your V3, this is going to be multiplied by V2, and this is going to be multiplied by V1. Okay, so that's the equation which you're going to get here. Okay, so by inverting op-amp, we know this equation and we have put into this, and these two equations are the same. So what I mean is, if you know the formula for inverting op-amp, you can find out the formula for this summer op-amp. Okay, now let's move on to the next. Next we have non-inverting summer op-amp, and it is non-inverting. That means we are giving the inputs to the non-inverting side, and feedback path is provided to the negative side. Rest of the things are same. And then we have this additional resistance because this is a non-inverting amplifier, so it's supposed to be like this. Okay, all right. KCL at non-inverting input and at inverting input. So let's see. So we are going to find out the KCL in case whenever you have non-inverting op-amp. Just remember you will be having two KCL equation. One, you will be applying the KCL at this V positive node and at this V negative node. Okay, so maybe let's name these. Let's name this as maybe V positive, and let this be V negative node. Okay, so V positive and V negative node. So that means we are going to apply the KVL into this node, and you see at this V plus node we have four currents at this node. I1, I2, I3 are going in, and I dash is going out. I dash is going to be 0. And then you have this V negative node, and so one branch is going to be here, and IA current is flowing here, and then you have feedback current going in here. Okay, and then by the principle of an op-amp, ideal op-amp, this voltage will be equal to this voltage, right? So let's find out the current equation. So I1 plus I2 plus I3 equals to 0 at a non-inverting input. So I1 is V1 minus V plus upon R1. So you understand this thing. We have this V1, so V1 minus V plus upon R1, V2 minus V plus upon R2, and V3 minus V plus upon R3. That's the same thing you have got. And the KCL at the inverting input, so you have here, so we are applying the KCL at this node, V negative. Okay, so at V negative we say V negative minus V0 upon RA, and then V negative minus V naught upon RF is your IF. So V negative minus V out upon RF is your IF, V negative, and then IA is equals to V negative upon RA. So now you have these two current equations. What you're going to do is you're going to put these into this above formula. So in this first formula, IF plus IA is equals to 0. And then putting into this formula, you will basically get this equation. So maybe you can pause the video and try to plug in these equation into this above equation, and then see if you are getting the same results or not. Okay, so the next thing what we are going to do after this, we have V negative equation, and then we have one equation from here. And then what we are going to do is we are going to put V negative is equals to V plus. So this V plus, you can basically, when you put all these three equation into this, and then you can find out the value of V positive, and then we will put that equation equals to this V negative, this equation to this equation. Okay. Why we are doing this? The reason, because you know that this is the infinite input resistance, so that means V negative is equals to, sorry, this, because of the infinite gain, this V negative will be equal to V positive, or you can say by virtual ground this V plus is equals to V negative. So here you'll put all the values of these currents into this equation, which is equals to 0. When you put the values, you see here it says V1 minus V plus upon R1. You can and then these are the same equation with different resistance and this input voltage. So if you see, you can also write as V1 by R1 minus V plus by R1. So what I mean is, or maybe I should write here. So this equation, I think I'll write here only. So you can either write this equation as, so V1 upon R1 minus V plus divided by R1. So you understand that this, you can also write in this way, V1 by R1 minus V plus by R1. So if you do that, the same, if you do the same thing, okay. So I hope you understand. I don't have to write it again, but you understand you can write in terms of V1 by R1 minus V plus by R1. And that's what they have done here. So you will get negative V plus by R1. So you can take it on the other side in this equation. That's what they have done here. V1 by R1 plus V2 by R2 plus V3 by R3 is equals to this term, which was the negative here, taken out here, this side. And then this is a parallel combination of a resistance. So we can take it as 1 by RT. So if you take as 1 by RT, you can take it on this side of the equation. Okay, so what they have done, so if you take it into this side of the equation, you will have V positive will be equal to V1 by R1 plus V2 by R2 plus V3 by R3 whole bracket into 1 by RT. Okay, so that equation is equated to this V negative, which is RA by RA plus RF into V out. So that's the same thing. You will get this. So RT has been basically taken here itself, and then you have to find out the value of output voltage. So ultimately you will get this equation. Again, if you don't understand how we have obtained the final equation, just pause this video and try to solve the equation by yourself. It's very easy. All the steps are mentioned here. You just have to rewrite and maybe simplify more in order to understand. Okay. Now let's see next. So this is another type of operational amplifier, and it's called difference op-amp. So as its name suggests, the difference. So what we are going to observe at the output, we are going to observe the difference of the input voltage at the output. And if you see in this particular operational amplifier, we are giving two inputs to each input. Right? So far what we have seen, either we were giving the input voltage to the positive side or the negative side. So when we were giving the input voltage to the negative side, then that was your inverting operational amplifier. And when you were giving the input voltage to the positive side, then that's called your non-inverting op-amp. But now in the difference op-amp, you are giving the two inputs to these two terminal of the, or two inputs of this op-amp. And then this R1 and R3 are the resistances, and this R2 is the feedback resistance. So let's apply the KCL at this node and at this node. The current going in here is 0 by the principle of infinite input impedance. So let's see the KCL at node VB. Let's first see for this one for VB node. So that will be your VB minus V2 upon R3. It will be equal to VB by R4, VB by R4. Or you can say that these two currents are going in and this is going out. So sum of these two will be equal to this. So and the important thing is you should know the fundamentals, like how the equation is can be applied. So uh, so here we have VB minus V2 upon R3 is equals to VB minus VB divided by R4. And then same here. So so let's first simplify this. VB will come out to be R4 upon R1 plus R4, R3 plus R4 into V2. Now what is V2? V2 is the input voltage here in this. So that's your input voltage V2. And this will be equal to VA. VA is what? VA is this voltage. The reason why, because by virtual ground, we know that VA is equals to VB. So these two are going to be equal. So that's why we have made this, the whatever we have found value for VB equals to VA. Now the next step would be to apply the KCL at this VA node. So let's see here, the KCL at node VA. So that will be your VA minus V1 upon R1 plus VA minus V0 upon R2. And that's what you see here is equals to 0. And then simplifying this equation and finding out the equation in terms of output voltage. So you will get 1 by R1 V0 is equals to 1 bracket 1 by R1 plus 1 by R2 multiplied to VA minus 1 by R1 V1. So just simplify this, the first equation and find out in terms of V0. So at the end you will get this equation 1. So when you simplify finally, V0 will be equal to 1 plus R2 divided by R1 VA minus R2 by R1 V1. So value of VA we already know. How? Because we calculated the VB in the previous slide here, and VB is equals to VA, which means it is equals to R4 by R3 plus R4 into V2. All right, so just put that value over here and then simplify further, and after finally simplifying you will get equation something like this. So this is the final equation. Okay, so you will get this particular equation, this final equation you will get. How light go? Okay, so this equation, final equation, you will get V0 is equals to R2 by R1, and then above numerator R1 by R2 plus 1 upon denominator R3 divided by R4 plus 1 into V2 minus R2 by R1 into V1. So that's your final equation for a difference op-amp. So since a difference must reject a signal common to the two inputs, the amplifier must have the property that V0 is equals to 0 when V1 is equals to V2. And this implies that R1 is equals to, R1 by R2 is equals to R3 by R4. This means is the difference op-amp will work properly if the attenuation network, so this is the attenuation network resistors, your this R3, R4, when they are related to the feedback resistor, your feedback resistor R1 and R2. So this R1 and this feedback resistor R2, in this way, where this in this way it should relate, where R1 by R2 must be equal to R3 by R4. They should have the same ratio. So if you have this, Then what does this mean? This means that your difference op amp, it will reject a common signal to the two inputs, and so you can assume that, if you assume that when R1 is equal to R2 and R3 is equal to R4, so put that value into this, make these some of the resistances equal, and if you put that value, then you are going to get V0 is equals to V2 minus V1. And if you get this value, then this is your subtractor. This is why this is a subtractor, because if you see, it is subtracting the two input. V2 is the input and V1 is the input. It is subtracting these two input. So this way you can basically make a subtractor. And next is the interconnection of op amps. So let's say you have three-stage op amp connected. So this is one stage of op amp, second stage, and the third stage. And at the output, you are getting V2 is equals to A1, V1, V3 is equals to A2, V2, and then at the third, at the this V0, you will get V0 is equals to A3, V3. So you can, like, this type of interconnection is also used where you connect them in series, the op amps, to get the higher voltage gain. Okay. Now this is an example circuit. You have to find the voltage transfer equation of this particular circuit. So you can just pause the video and try to find it out. And I'll end this lecture with this last slide, and for you to basically pause it and try to see what is happening in this particular circuit. And it's the same circuit which is not the same circuit, but based on this particular principle, where these are the three-stage op amp, and if you use this formula, you can easily calculate the output voltage. Okay, so this is it for today. Thank you so much for watching.